Hello everyone, let's continue with our general chemistry class course. And today we're going to talk about a topic that I really like a lot, which is called thermodynamics. Right? What does that mean? Well, how the temperature, or more accurate, the energy, is going to move through a system, okay? And thermodynamics actually is something pretty cool. It's something that we know that it works basically all around the universe. Okay, I think it's one of the models in science that it's not going to change a lot forever. I might be wrong, but it's possible that it will not, because it's very consistent, right? Something that we really know that it is very true. But that's not something quite so good, right? Because if it's constant in the whole universe, that means that we have a problem, because then we would have to study the whole universe. Well, actually, we can be more accurate, right, about what we are saying. And instead of saying that I'm going to study the whole universe, right, what I'm going to say is that I'm going to study a fraction of the universe, which is very different, right? And I can decide which fraction of that universe I am going to study. So basically what I am going to do here is that I will set the limits, right, of what I want to study. And the subject of study that I want to define right now, it is called the system. Okay, so when we talk about system in thermodynamics, actually what we're talking about is the fraction of what? Of the whole universe that I want to study. Very well. And the system, it's important that although it has limits, right, the ones that we have already set for it, it's also in interaction with what? With everything around it. So we're going to call this the surroundings. And this is the model that we're going to use, right? A fraction of the universe that I want to study, which is going to be called system, and it's going to be in interaction with the surroundings. Okay? Why? Because heat, the part of thermo in the word, is going to interact through what? Through the system, surroundings, system, surroundings, system, surroundings. Very well. So let's continue with that. Very well. So now let's talk about a concept that it's called energy. What is energy? Well, basically it's a very difficult word to define. I would call it like a primitive concept, that it's something that we know that it exists, we cannot define, but we know that it's there, pretty similar to time. Right, but I'm going to try to do the best that I can to explain it, and I would say that it's the other coin of mass, right? The other side of the coin of mass. I would say that energy is everything, and that makes something work out. Let's call it like that, right? And a system like this one, right, has energy. You can consider yourselves as a system that has energy. Yes, absolutely. Living cells are systems, right? The stars, galaxies, everything, those systems have energy. Very well. And if we're going to define them in the classical way of thermodynamics, we have to understand the fact that this energy is going to be divided into different things. The first one in heat, and the other one in work. Okay, so basically those are the two concepts that will define as a whole the energy of a system. Very well. So we have to start depicting these as symbols, right? In which we can use later to create an equation. So I'm going to call energy actually as what? As the internal energy of the system, right? Which is nothing but the proper energy that the system has. And I'm going to depict this as just a capital U. Okay, and heat, well, we're going to use the letter that we've been using since a while. We're going to keep calling it Q, right? And work is going to be depicted as the word W. Very well. So the whole energy of the system, the internal energy of the system, the energy that the system has by itself is going to be what? Well, the contribution of heat and the contribution of work. So the contribution of heat and the contribution of work. Very well. So let's continue with that. Let me check my notes. Very well. So if we're talking about heat and work, we can say that we can apply heat to the system, or we can also take heat from the system, right? And we can also say that we can apply work to the system, or that the system can apply work to something else, meaning that the system will apply work to the surroundings, meaning that the application of the change of heat, we can track it as if we were talking about the change of temperature, and the work and the change of work, we're going to define it as the change of volume. Okay, so remember, if you have a piston, right, and you want to apply a work to the system, meaning that the system is your piston, right, we have to apply pressure, and what is going to change is the volume, right, because after some time that we apply energy, the volume in this case is going to diminish. So we're going to define work right now as the change of volume. And you can see that these two variables are quite correlated to the idea of ideal gases. So eventually these two are going to be related to what? To the change of pressure. Very well. So let's draw again the system, the representation of the system that we were trying to define a moment ago. Very well. And let's see how the energy is going to work from the surroundings to the system, and to the system from the surroundings. So, for example, the surroundings can have heat on them, and they can apply heat into the system. Okay? Or the other way around is if the system can release heat out to the surroundings. Okay, in the same way I can have also what? Work that comes from the surroundings, and I can apply this on the system, or the system can apply work to the surroundings. So it's going to be work applied by the system to the surroundings. Very well. So in these terms, what happens with the internal energy? Because now we're doing what? Changes of heat and changes of work. So we have to define what is going to happen with the internal energy. Why? Remember that U is the same as Q plus W. So if I do changes in Q and W, I'm also going to have changes where? In the internal energy. So let's go and say that if you apply heat in the system and apply work on the system, right, for sure the internal energy is going to increase. Now if in the other way you take heat out of the system and work is applied by the system, what is going to happen is that internal energy of the system is going to diminish. Okay, so what does that mean? Well, that means that depending on how the heat flows or the work flows in one direction or another, right, the internal energy can either increase or decrease. Very well. So let's go now and talk about a different concept, which is called enthalpy. Okay? And enthalpy has a thermodynamical definition, which is very simple. Enthalpy is going to be defined as H, and it's going to be an addition of the internal energy plus the pressure times the volume of the system. So we're talking about the enthalpy of what? Of the system. Very well. And that means that the enthalpy of the system will be a function of what? Of the internal energy of the system plus the contribution of pressure and volume of what? Of also the system. So we're talking about specifically of gases, but these can also be applied to many other things. You will see in a moment why. Very well. So if I want to apply changes to what? To the system, that means that the change of H can also be applied, right? I can also have changes in the internal energy, and for the most I know also that then I'm going to have to apply changes to either pressure or volume. And in this case, what I'm going to do is that I'm going to choose to apply changes on the volume. Why? Well, you will see in a moment. So let's talk about PV and make a dimensional analysis for this. So I'm going to put an equivalency and say that define pressure first. So pressure is nothing but a force that is contained inside of an area, or a force that is applied to an area, right? And volume, right, is nothing but the length in 3 dimensions, right? For example, for a cube. But if you're observative enough, you will find out immediately that actually what you have here is what? An area, right? Because distance times distance is the same as area. So once we perform a dimensional analysis, we see that these two will cancel this area. So the same thing, we can say that PV is the same as what? As a force times length. But if you remember your classes, right, of Physics 1, work is the same as what? As force times the distance. And what is the length? It's another way in which I can call distance. So pressure times volume is the same as what? As a force times a distance. And this is the same as what? As work. Okay? So you can see that if I multiply pressure times volume, actually what I am doing is defining a way of work. Very well. So let's go and write this again. PV is the same as force times distance, and this is the same as work. And it's very important to say that this work is going to be applied by the system. So we need to make a direction. In this case, since it's applied by the system, this work is going to have a negative sign. Why negative? Because with the minus sign, I'm going to say that it's being applied by the system, not towards the system, but the work is from the system to the surroundings. Okay? Very well. So if this is true, what I can tell now is that if I have a change in the internal energy, right, I would have to say that I have Q plus work. Okay? Or I can also say that if I have a change of H, this would be the change of U times P, the change of B. Very well. But look at this. This U is the same as what? As this U. And this PB, P times the change of B gives the change of B is going to be what? Minus W. Why? Because I can apply here a change whenever I want. Very well. So let's go and make the substitution of this change of U here. Right? Because this U is this U and this U are these two. Right? And then this B times B is what? Minus W. So let's go just put this plus into parentheses what? Minus W. So you can see that this W will cancel this W, and then I can say that the change of H in a system basically is going to be what? The full and pure amount of heat. Very well, I think the video is already long enough, so I'm going to stop it here, and I'll see you next time. Goodbye.